Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples. Hello, and welcome back to another episode of Stories from Space. I'm your host, Matt Williams, and today we're going to delve once again into Fermi's paradox, asking the question, if life is in fact abundant in the universe, and we have every reason to think it is, then why is it that humanity hasn't found any evidence of extraterrestrial life or intelligence? At least not yet. In previous installments, we looked at various proposed resolutions. This included the Hart-Tipler conjecture, which states that the absence of evidence can only be explained by the non-existence of extraterrestrial intelligence. We also looked at the possibility that the reason for the Great Silence is because all extraterrestrial civilizations have been periodically wiped out, perhaps by cosmological phenomenon like gamma ray bursts or supernova, or by hunter-killer robots, which were essentially von Neumann probes that either went berserk or were programmed by their malicious creators in order to wipe out intelligent life before it could become a threat to them. We've also examined how extraterrestrial intelligence, far in advance of ourselves, may be taking great pains to avoid us and remain hidden from our instruments. Or it could be that we just haven't found any yet because making your way across space, expanding, growing, it's difficult, or it's not something that advanced species really want to do. Well, today, we're going to take a look at another proposed resolution known as the rare Earth hypothesis. And this theory basically comes down to two central premises. One, microbial life is common in planetary systems, and two, advanced life, which is to say complex life forms that could eventually give rise to sentient creatures, is rare. And in this respect, the rare Earth hypothesis is not unlike the Great Filter hypothesis, which essentially states that there may be something in the universe that is preventing life from evolving, either in the early stages of life, where single-celled bacteria are concerned, or in the later stages of life, where cells develop complexity, mitochondria, sexual reproduction, eventually giving rise to intelligent creatures that could someday be capable of establishing outposts of their civilization among the stars. And the term rare earth comes from the book Rare Earth: Why Complex Life is Uncommon in the Universe, which was written by Peter Ward and Donald E. Brownlee in the year 2000. Ward and Brownlee are professors of paleontology and astronomy, respectively, at the University of Washington. They are members of its astrobiology program, and Brownlee has also had the distinction of being the principal investigator of NASA's Stardust asteroid sample return mission. And their argument was basically made in response to what they saw as the inherent assumptions and biases of the Drake equation, which, as we know from a previous episode, was the brainchild of former astronomer Frank Drake, which he wrote out in 1961 in preparation for the very first SETI conference ever. And while the equation was meant to encapsulate the challenges that SETI scientists face, Ward and Brownlee believed that it made the assumption that intelligent life should be plentiful in the universe. And as I argued in that same previous episode, this is a possible takeaway from the Drake equation, because even when all of the parameters of it are estimated very conservatively, you still come out with a number that is encouraging, that would suggest that there are at least a few, if not at least one, civilization out there in the galaxy at any given time that we could communicate with. And this was certainly their take. As they explained in their book, the solution to the Drake equation includes hidden assumptions that need to be examined. Most important, it assumes that once life originates on a planet, it evolves towards ever higher complexity, culminating on many planets in the development of culture. This is certainly what happened on Earth. Life originated here about 4 billion years ago and then evolved from single-celled organisms to multicellular creatures with tissues and organs, climaxing in animals and higher plants. Is this particular history of life one of increasing complexity to an animal grade of evolution, an inevitable result of evolution, or even a common one? Might it, in fact, be a very rare result? Another point this raises is the Copernican principle, or the mediocrity principle, named after famed astronomer Nicholas Copernicus. This principle, which bears his name, argues that humanity and Earth are not privileged observers, they are not special in terms of space, place, or time, and that our situation is representative of the universe. So it's also known as the mediocrity principle because it's essentially stating that if something is sampled randomly, it is likely to be representative of the majority rather than being unique or special. And astronomers and cosmologists certainly have reason to believe that this is the case when looking at the wider universe. After all, decades of observation have confirmed that the universe is isotropic, meaning that it is very much the same in all directions. On the macroscopic scale, matter and the ingredients for life appear to be distributed everywhere in abundance. And our observations have also indicated that it's expanding in all directions at the same ever-increasing speed, or what is attributed to dark energy. So when it comes to planetary science, this principle essentially argues that Earth-like planets must be common in our universe. However, what if that's not the case? What if Earth is actually not representative of the whole and is actually an outlier? If that is the case, then Earth-like planets, such as our own, are even more rare than we give them credit for, and far, far more precious. And there is some scientific evidence to back this up. For example, in the realm of exoplanet studies, scientists have now confirmed the presence of 5,566 exoplanets beyond our solar system. Now, of these, the vast majority are Neptune-like, meaning consistent in size and mass to planet Neptune, are gas giants of the varieties of Jupiter-like, Saturn-like, super Jupiters, hot Jupiters, or super Earths, which are basically rocky planets many times the size and mass of Earth. Only a small minority, 199 so far, of these confirmed planets have been identified as terrestrial, which is to say Earth-like. They're composed of silicate minerals and metals, most likely differentiated between a metallic core and a silicate mantle and crust. However, the concept of the rare Earth goes far beyond merely being Earth-like in composition. It also goes down to our atmosphere and how it has evolved over time. As we've known for some time, Earth did not emerge with its current atmosphere. Its primordial atmosphere was composed of the same gases as the stellar nebula which formed our Sun and our system of planets, meaning that it was predominantly composed of hydrogen, as well as water vapor, methane, and ammonia, which is similar in composition to what we see with the gas giants like Jupiter and Saturn today. Our second atmosphere, which gradually formed as the Earth cooled and volcanic activity was very common, consisted mainly of volcanic outgassing and also large asteroid impacts during the late heavy bombardment, which deposited all kinds of gases and volatiles here on Earth. So the atmosphere was largely composed of nitrogen, carbon dioxide, and various other trace gases such as sulfur dioxide, sulfur monoxide, that were consistent with volcanic eruptions, and water vapor. And it was only over time, thanks to the emergence of single-celled bacteria and photosynthesis, that the oxygen content of our atmosphere began to gradually increase. And over time, this created our current atmosphere, which is still nitrogen dominant. Roughly 78% of our atmosphere is nitrogen gas, 21% is oxygen gas, and the remaining 1% is trace gases such as carbon dioxide, which is an important greenhouse gas which helps our climate maintain stability over time. So basically, Earth has gone through a number of transitions. It went from being what was, by our standards, an uninhabitable world with a choking atmosphere, but which facilitated the emergence of early life, to one that is surrounded by a fluffy atmosphere composed of nitrogen and oxygen. And interestingly enough, this oxygen atmosphere especially during the Great Oxidation Event when oxygen levels were much higher. This would be fatal to primitive life forms such as cyanobacteria and other life forms today. So, in fact, if we found exoplanets out there that had a rich oxygen atmosphere, we would naturally assume that life could exist there because of the importance of oxygen for all complex life forms. But if life has not already emerged on that planet, if we're looking at abiotic oxygen, oxygen that's produced through chemical effects that are not biological in nature, then life as we know it would not be likely to emerge. Certainly not along the same lines that it did here on Earth. So when looking for planets that we believe would be habitable, aka Earth-like planets, we also have to wonder, are the conditions just right and are they right at the right time? And could it be that Earth also has several advantages that other Earth-like planets don't? In particular, astronomers have noted that the presence of a massive gas giant like Jupiter in the outer solar system has helped protect Earth from impactors in the past. Its powerful gravity manages to scoop up most of the asteroids that are hurling through the system, not to mention interstellar asteroids that are also entering the system. They get captured by Jupiter's gravity and are either brought into its orbit or they crash into its surface. Those few that have slipped through over many eons have led to extinction-level events, so one could easily imagine that if Earth weren't protected by a massive gas giant, that life would have been systematically wiped out by one extinction-level event after another. So these and other considerations led Warren and Brownlee to conclude that perhaps life here on Earth is very privileged. It's special because it has enjoyed all the right combination of elements and requirements that have fostered evolution over time, and that these same conditions may not be prevalent throughout the universe. And this is one thing that they took the Drake equation to task for, which was the assumption that intelligent life should be plentiful. So in response, they produced their own rare earth equation, in which they considered all the things that go into making life here on Earth as a way of illustrating how special a rare Earth may be. And in this equation, which was similar to Drake's in that it began with N, the number of advanced civilizations out there that we may be able to communicate with someday, that this could be determined by multiplying the usual parameters of the Drake equation, such as the average rate of star formation in our galaxy, the number of stars that have planets, and so forth. But they included a few others. For one, they included the galactic habitable zone, so the fraction of stars that are within that. And that refers to the band in our Milky Way that is neither too close towards the center, where radiation is much more intense, nor too far out at the periphery, where star formation is much more common, thereby blasting out a lot of radiation. They also included a parameter which considered the planet's lifespan where complex life is present, which, using humanity as an example, is a very small fraction of the time. They also included planets with a large moon, which is highly relevant because modern research has shown that the presence of our moon, that it has an effect on Earth's magnetic field, thus protecting it from cosmic radiation and solar radiation, and that it has also absorbed a lot of impacts for us. And so, of course, they also included a parameter for the existence of a large gas giant in the outer reaches of the system, as well as the number of planets with a low number of extinction events. In addition, Ward and Brownlee listed 3 other factors that are particular to Earth and that have been rarely observed with other planetary bodies, even with the huge number of exoplanets that have been discovered in recent years. And these include plate tectonics, which have been fundamental to climate stability here on Earth. They are a major part of the carbon cycle in that it periodically releases carbon through volcanic activity, but also sequesters carbon in the form of carbonate rocks. And this is what has ensured relatively stable levels of CO2 in our atmosphere over time and ensured climate stability over time. Second, they cited the geological evidence that indicates that twice in our planet's history, there was an exception to this rule where Earth was very cold and covered in ice. And these are known as the snowball Earth epochs. And the first occurred roughly 2.2 billion years ago, the other roughly 635 million years ago. And they both coincided with the key developments in terrestrial life. The first coincided with the evolution of photosynthetic life. which, as noted, was responsible for converting our atmosphere into something breathable by our standards. And the latter epoch coincided with the Cambrian explosion, which refers to an extended period where there was a burst of species diversification and the appearance of almost all animal taxonomies that exist in the fossil record today. Third, they argued the then popular idea that life may have evolved on Mars prior to Earth and been transported via lithopanspermia, which could mean that an Earth-like planet, unless it has a Mars-like planet next door, would not be seeded with life and would not therefore be able to evolve it. So when you factor all these additional requirements in, the whole notion of probabilities begins to become much, much smaller and slimmer. As I said before, one of the benefits, one of the high points of the Drake equation was that even if you factored very conservatively with all the parameters he named, you still got an encouraging number at the end of it. A non-zero sum, basically. But when you factor in all the other considerations, then the results are not so encouraging. In fact, you end up with some paltry outcomes that show that there may very well be no other intelligent civilizations out there in the galaxy right now that we are capable of communicating with. But of course, there is a flip side to this coin, which includes the fact that, much like the Drake equation, the rare Earth hypothesis and its equation are subject to a lot of uncertainty. For example, when Ward and Brownlee published their study in 2000, there were less than 10 exoplanets in the exoplanet catalog, whereas today there's over 5,000. And this has helped remove a great deal of the uncertainty when it came to the parameter involving the number of planets per star in the Milky Way and the percentage of those that orbit within the habitable zone. And while the number of rocky planets that are similar in size to Earth is somewhat limited in the catalog right now, astronomers suspect that this has to do with the limits of our current instrumentation, that it is far easier to spot larger planets with more distant orbits rather than smaller rocky ones that are orbiting more closely to their sun, which is where we would expect Earth analogs to be. And of course, this is changing with the deployment of the James Webb Space Telescope, and will continue to change as more next-generation observatories become operational. Second, there's the issue of plate tectonics, which had not been observed on any planet other than Earth in Ward and Brownlee's time, but have since been observed by missions like New Horizons, which noticed features on Pluto and Charon that were indicative of icy plate tectonics. And the same holds true for icy moons like Europa and Enceladus and Titan, all of which experience a form of tectonic activity in the way that their surfaces are constantly being renewed through exchanges between the interior and the surface, which is precisely how plate tectonics work here on Earth. And there's also multiple lines of evidence that indicate that though they may be geologically inert today, planets like Mars may have been geologically active in the past, and still are today to a significantly less extent. In addition, there is modern research that indicates that stagnant lid planets, or planets that don't have plate tectonics, that it's possible that life could still emerge on these worlds. Third, it's not clear whether or not large moons are a rare occurrence in our galaxy. For example, the giant impact hypothesis, which is the predominant view of how the Earth-Moon system formed, states that several billion years ago, shortly after the formation of the solar system, a massive planetoid named Theia collided with the primordial Earth, and the resulting debris that was liquefied and thrown out that formed into two separate bodies, the Earth and the Moon, which then established a stable orbit. Now, according to recent research, it's been theorized that this impactor, Theia, may have actually formed in a stable orbit at Earth's Lagrange point, which would mean that such objects and impacts, which could result in the formation of a large moon, are really not that rare, especially when a solar system is still in formation and the orbits are being established. And what's more, the idea that Jupiter has actually prevented Earth from receiving impacts, while there certainly is plenty of evidence to show that, which include many impacts that have been observed by astronomers in recent decades, there is research that shows that over time, Jupiter's gravitational influence may have actually attracted impactors or knocked asteroids loose from the main asteroid belt that would have threatened Earth over time. And of course, there is always the very, very difficult notion of habitability and what defines it. And with the recent spate of exoplanet discoveries, scientists have been questioning and refining the notion of what constitutes a habitable planet. They've, for example, questioned whether or not Earth constitutes the gold standard, whether or not there are planets out there that are significantly more habitable, and also what constitutes the range of a habitable zone, whether it might be narrower or more extensive than we thought, depending upon planetary conditions. So, once again, the rare Earth hypothesis suffers from a range of uncertainty, and it reinforces the fact that one of the main barriers, one of the main challenges when it comes to answering the question of how plentiful is life out there, or are there any other civilizations out there in the galaxy right now? What is the probability? What are the odds? This suffers from a lack of data. And while we've gotten better at constraining certain parameters in the Drake equation, the rest are still very, very uncertain to us. We have no idea if life can emerge under conditions other than what we are familiar with. We have no idea how often that is likely to occur. We also have absolutely no idea how likely it is that intelligent life will emerge and whether or not that intelligence is one that we could actually communicate with or even recognize. So once again, it all comes down to a whole lot of unknowns. And so when we consider the Frank Tipler conjecture, which states that there is no evidence for extraterrestrial life, ergo one must conclude that doesn't exist, one has to question how they arrived at such a fatalistic conclusion. Even after 60 years, the search for extraterrestrial intelligence and the field of astrobiology, they remain incredibly data poor. For signs of technosignatures within our galaxy, we have peeked under many rocks within the solar system. And yet we have barely even begun to scratch the surface. And on top of that, we really have no idea what we're looking for when we consider extraterrestrial intelligence and extraterrestrial life in distant solar systems. There could be a plethora of possibilities we would never even consider because we simply haven't seen it yet. But our methods have come a long way, and there are a lot of exciting missions in the future and experiments where SETI is concerned that could help increase the odds and narrow the search parameters and even expand our frame of reference. In short, until we get a better idea of just how common Earth-like planets are, and if in fact Earth-like conditions, which have evolved as noted, are necessary for life to emerge, the Drake equation and the rare Earth equation are going to remain subject to a tremendous amount of uncertainty. And that's something, at least if you're a keen student of astrobiology or someone who is hopeful that we find evidence of life beyond Earth someday soon, that's what makes the coming years really very exciting. Because with so many missions looking for it, and not just on Mars anymore, but also Venus and Jupiter's icy moons and Saturn's icy moons, we stand a much better chance of actually answering the question, is there life beyond Earth? And with next-generation telescopes like James Webb and the Nancy Grace Roman Space Telescope, and projects like Breakthrough Listen, the odds of us detecting something which could be said to be a possible technosignature, they're going to increase too. And with observatories like Vera C. Rubin and the Galileo project becoming operational, we're also likely to hear a great deal more about all those interstellar objects that periodically enter our system, some of which stay, and all those unidentified aerial phenomenon, UAP, that are constantly being spotted in our atmosphere. So while we may not be able to say what the likelihood of there being life beyond Earth is, or the likelihood of there being intelligent civilizations in our galaxy are, we can safely say that the odds of us finding evidence will be significantly greater in the coming years, far greater than it's been since the dawn of the space age and the first SETI experiments were ever conducted. That may be the best that we can expect for now, but it is still very encouraging, and it's going to be very exciting to see how that all unfolds in the coming years and decades. Tune in next time when we will be speaking to Stephen Vance, the Deputy Manager for the Planetary Science Section at NASA's Jet Propulsion Laboratory, who will speak to us about his work on the Europa Clipper mission and how it will be traveling to Jupiter's icy moon in the coming years to investigate the possibility that there may be life beneath its icy surface. In the meantime, thank you for listening. I'm Matt Williams, and this has been Stories from Space.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.